Hi guys, today we're going to look at 11.2 growth and decay. And basically we're putting differential equation into use of our daily life, more specifically in scientific life. And the first one we're going to look at is the law of natural growth, which is dy dx is equal to ky. That's our type 2. Our type 2 differential equation. And to solve type 2 differential equation, we know we're gonna invert. Okay, we're gonna invert both sides. Okay, for example, here the derivative is proportional to the fraction itself. Dx dy is equal to 1 over ky. So to solve that, as I said, you gotta invert both sides, and x is going to be equal to that. Don't forget this is absolute value of y. And after that, you can combine x and c and times k, rearrange to get this one. And then you have your absolute value of y is equal to e to the power of k bracket x minus c. You expand this, you expand this index. This is in index form, you can expand it. And then you have that, and we're letting this is equal to 8. So letting this is equal to 8. We have y is equal to a e to the kx. Therefore, dy dx is equal to k a e to the kx, and that's ky, which has proved we have done it right. Okay, so that's a check, because y is equal to that, and dy dx is k a e to the kx, and that's ky. Population growth, the rate of increase of population is proportional to the current population at the time. So normally we use n to mean number of population, okay, and n of t, that's a function of t. That's the population number. And dn dt is directly proportional to n, which means dn dt is kn, where k is a positive constant. And the solution to this differential equation, as seen previously, so as we've seen from here, we found n is actually n naught times e to the kt. And n naught is your initial population, and the k is the annual growth rate. Okay. Although n is treated as a continuous variable and graphed as such, it is really a discrete quantity, and final answers often have to be rounded to the nearest whole number. Okay, final answer often have to be rounded to the nearest whole number, which means we could use calculator. Okay, we could use calculator. In your exam, you don't really see this kind of question in your exam 1. It's most likely will be appeared in exam 2. So feel free to use your calculator. And this one told us we're expecting a whole number, and it's fine for us to use calculator in the middle of solving the question. Okay, so you don't have to worry about the precision when you are using calculator during the steps. I elaborate more when I'm explaining the question. So example, the number of frogs in a colony increases at a rate proportional to the current number. After 15 months, there are 297 frogs present, and this number grows to 523 after 26 months. Determine the initial number of frogs present in the colony. Okay, so again, we know number of population, dm dt, that's directly proportional to n. Okay, this is from here. All right, the population is directly proportional to the current population, n. Okay, so once you get here, from previous result, we're gonna know after solving this differential equation, you're gonna have n is equal to n naught times e to the kt. Okay, so that's like a shortcut for you. N is equal to n naught times e to the kt. And then we can solve a simultaneous equation by putting those given information. So first piece of information, after 15 months, there are 297 frogs. 297 is equal to, and no, we don't know, e to the kt, e to the k, and the t would be 15 months. Okay, that's our first equation. And the second equation, 523 is equal to n naught e to the power of k times 26 months, 26. All right, by putting this into your calculator, I've got the answer straight away. Your n naught is going to be 137, okay? Approximately 137. So this is solving simultaneous equation, and our variables are n naught and k. Okay. Radioactive decay. The rate of decay of radioactive substance is proportional to the mass of the substance present at the time. And this is a decay. So whenever you heard of decay, that means you're going to put a minus sign. All right. So the negative dm dt, this negative gradient, this negative rate is proportional to m. So dm dt is equal to negative km. All right. To solve that, similarly, you're going to have a conclusion. Having invert them, invert them, and then you integrate with respect to m for both sides. You're going to have m is equal to m naught times e to the negative kt. And m naught means when t is equal to 0. And the half-lives, this life is a bit different from what you usually mean. What it usually means, it means the mass is half. Okay, so the half-life t is the time it takes for half of the original mass to decay. So to determine the value of t, we're gonna solve that. That's what we've solved. We've got from here. And in this case, your m is half of m naught, your initial mass, and t is equal to capital T, which means the t we're looking for. So half m naught is equal to m naught times e to the power of negative kt. E to the negative kt is 1/2 negative kt log e 1/2. T is equal to that. Okay. Example, the rate of decay of a radioactive substance is proportional to the amount of the substance present at that time. Initially, 80 milligrams of the substance is present, and after 1 hour, it observed that 10% has decayed. Determine the amount remaining after further 2 hours. Okay, remember, when you're talking about decay, okay, about the substance, it's about the mass. It's about the mass. So it says 10% has decayed, which means the mass has been reduced by 10%. So 80 times 90%. So that's 72 milligrams. So that's the mass after 1 hour for the substance. Okay. Again, we've got the formula m is equal to m naught e to the power of negative kt. Okay, negative kt because it's a decay. And then we're going to substitute our values. So first piece of information, 80 milligrams of the substance is present after 1 hour. And we know it's talking about hours, so we just kind of assume the units of time would be hours. So the first one, m is 80, is equal to m naught, we don't know, times e to the power of negative k, we don't know, times t. T is at this time is after 1 hour, so times 1. And then 72, oh, hang on. Initially 80 milligram. Oh, my bad. It's initially, which means actually we know our m naught it's going to be 80. Okay, m naught it's gonna be 80. M naught is gonna be 80. So that's the first piece of information. The second information, 72 after 1 hour. So 72 is equal to m naught 80 times e to the power of negative k times 1 hour, which gives us k is equal to natural logarithm 80 over 72. Okay. All right, remember, because we're going to correct our answer, so it's fine. You can leave this as a decimal. Decimal is fine. Okay, just make sure you don't correct to don't correct to whole numbers. You might correct it to about 4 to 5 decimal places to make it precise. Okay, there's not much use in this case because natural logarithm 80 over 72 is not too hard to write, but sometimes your answer could be very ugly, very complicated. If that's the case, you would better use decimal. Okay. Now, once we got these, the question is asking the amount remaining after further 2 hours, which means t is equal to 3 hours. Okay, based on the 1 hour, another 2 hours. So your m is equal to m naught 80 times e to the power of negative k. K is known natural logarithm 80 over 72 and times 3. And observe this for you. Your mass is going to be 58 milligrams. Okay, so after 3 hours, your substance is gonna, the mass of the substance is gonna be reduced to 58 milligrams. And that's the end of 11.2. Thank you.